Okay, so we're going to do slip sliding away, which is introducing us to glacier dynamics. So you've got your 3 cups, your borax solution that you mixed last night, got your bottle of glue, and I'll give everybody a second to get those close to you. So the first thing you're going to do is do a little bit of measuring. So you're going to take one of the empty cups and pour 100 milliliters of glue into it. And actually, it's going to, you have a little bit more than that in the bottle, but it's really hard to get it all out. So pour out as much as you possibly can. It comes very close to 100 milliliters of glue. You're also going to have 75 milliliters of water and your borax solution. So make sure you've got all of that next to you.
Lois, you said 75 milliliters of water, but if I remember at the directions, we're only like, I think 55 mils of water.
Now this is separate from the borax solution. You had 55 milliliters saturated borax, but you also need 75 milliliters of water.
Got it. I believe so.
Very close to 100 ml of glue.
Yeah, as close as you can get to 100 milliliters of glue. It'll come close if you shake the bottle a bit.
Is that distilled water or tap water?
I just use tap water. Now this recipe is on the paper that was in your bag, and I'll tell you how to do a classroom mix too later. We're just gonna make a little bit here. So what you're gonna do is pour your 75 milliliters of water into the glue, and you're gonna take the craft stick and stir it thoroughly. You wanna mix up the glue. Now, not the borax solution. This is plain water, water and glue. Stir it thoroughly with the craft stick, scrape the sides and the bottom while you're stirring. I'm not sure where y'all are. Maybe even open your microphones and tell me how you're doing. I see Russ's computer, but I can't get everybody on at once.
See if you can hold it up in front of your computer without spilling it down your keyboard. That would be a really bad thing, but
that would be bad.
Nice.
Okay, so once your glue and your water is mixed, the next part is, how many of you have made glacier goo or any kind of flubber or anything like that using borax and glue before? Has anybody done that? I don't hear anybody and I can't see everybody.
Yes.
Yes.
It's good to get some feedback. Oh my God, you feel like you're on
many times.
Okay, so the next step then is you're gonna splash some of the borax water into it and keep stirring with your stick. You're gonna stir until it starts to come together and pull away from the sides of the cup. And mine really stuck to the stick at that point, but just stir it all up. When it gets really, you keep splashing in a little more borax until it comes together really nicely.
How much of borax solution should I put in the glue? Like,
Splash and stir, just splash and stir until it starts to come together. You can, when it comes together, what I did was I pulled it off of the, probably should have told you to have some paper towels nearby or a rag, or you do need a rag, but we're gonna be patting it dry with a rag or a towel, but not with paper towels, but paper towels could wipe up water. You're gonna actually squeeze it with your hands and really get that borax solution mixed into it. That's looking good, Paramita. I see yours coming together. So squeeze it and squeeze it till it comes together. And when it's really come together and you feel like you're making a polymer, so when it gets all cross-linked, it doesn't stick to your hands anymore once it's really together. So I've got some here that I made this morning. I have a little bit more than you do, but because I made a bigger batch.
And then you can dry it off. If you have an old rag or something like that, you can actually dry it off with a rag. I wouldn't dry it with paper towel. Paper towel tends to stick.
Right, don't use a paper towel on it.
Use your good tablecloth, you know, your suit.
I have nothing here.
will this work?
Just a rag, just to kind of pat the water off of it. It's a good idea to have a rag. Now I gave you a piece of wax paper. Once you got it, and it's actually dry. It's not sticky if it's come together well for you.
If you still have any raw glue in there, just put a little bit more borax water in. The borax is a cross linker that'll connect all the glue molecules together.
And once it's all together,
Like a ball. It becomes like a ball.
we're going to actually use this tonight at the Science Cafe. So we just wanted to get it made up now. But I wanted to tell you that Bill is the glacier goo guru. Oh my goodness. He knows more about making glacier goo than
He's
anybody.
got to have a skill in life, you know?
So whoops, let me go. Oh, tell me.
Don't put
After
it
you
on
guys have your PhDs, I just know how to make, you know, goo.
Don't put it on a terry cloth towel.
No, no.
You said a rag. I got a
Oh, you're
rag.
right. I'm sorry. Oh,
It's okay. It's a rag.
yeah.
So I have a link on there that I'm gonna just want to show you if I can get my screen to
We're
cooperate
making
here.
it in a ball, huh?
Yeah, you can just make it
If you
a
get
ball.
money,
You
don't
can
put
set
it
it right on your wax paper. Later, if you put it into a Ziploc bag, it'll stay in your refrigerator for a long time.
So
So
what you might want to do is use maybe one of your pans here, and you can dump it into there, and then you can dry it off a little bit, and then dump it into another one of these bins. So
so
just start to get it isolated.
tonight, when we're back together after a long break, make sure you have your glacier goo and one of your graduated cylinder cups. And if you have the ability to take a time-lapse video, you might want to have your camera ready to do that tonight. If not, just you'll be able to snap some pictures. So did everybody make it successfully? Are you okay with it?
And we
Yes.
would love to have any selfies with you and your goo put up on the Padlet,
Do it again.
I need to get it out.
or kids at home with your goo.
Yeah.
Oh, this is a nice one tonight, Louise. Those are nice instructions.
Yeah, oh, good. I'm glad you like them. That's so good.
That's some nice goo.
Um,
Hey, if you have,
All right, so I'm just going to show you the goo guru here, if I can get my mouse back to the right
Okay.
place.
if you have goo, hold it up in front of you. Let me see your goo where it's at right now. Anybody else have goo? Ooh, oh, goo in a bag. Goo in a bag is better than goo in a hand. Is there a saying like that? I don't. Two goos in a bag is better than one goo in the hand, or
Uh, if you look at your screen, here's
Because if you're in a lab, you can use glassware to measure, or else if you're at home, you can just use some things like measuring cups. So
very famous person making goo there. And what he does is he makes enough for, in that video, for a classroom, a whole classroom set or a lab set of goo. It's a lot of goo. So a gallon of Elmer's glue. Nice stuff. So,
Can you post that link in the, I know it's on our website. Can you post that in the chat box? If they're keeping track at all. Yeah, that makes a gallon at a time. Or it actually makes about 2 gallons at a time because you use an entire gallon of glue. So Matt, I know Matt's not on the screen
you
right
guys
now, but if,
angle your camera so I could get some goo pictures while you guys are doing this. Thank you. Oh, that's a good one. Hold still. Let me get a video of that.
hold your goo up if you have it, everybody.
All right, hold on. I'm doing Chloe first because I got to adjust the screen. Hold on. I'm sorry.
I'm gonna do a class.
Okay, now we can do a class goo.
Goo class, hold up your goo. Ready, hold up your goo.
All right, I got to adjust my
Where's
frame.
Rose?
1 second.
Where's Rose? We
just
lost
don't
Rose.
drop it on that keyboard. We're not responsible. I think there was some fine print in
Thank you.
Louise's
Show me your
application
goo.
you signed.
I'm responsible.
All right, perfect. Thank you.
Okie dokie. So put that, have that, and one of the graduated cylinder cups for this evening. And this will completely catch us up if I can just show you this one thing. Mary was talking about the drills, and we do have a really nice drill model that one of the engineers worked with me. I had built a model, but it didn't travel very well. And he came up with this one. Well, never mind, I'll show you the real thing. The slide is not gonna, I'm really having a problem with my, it's telling me that my internet is unstable and I'm seeing that things are not showing up very well. Well, you can see my screen. So I'm just gonna show you the actual model. You have the directions and this nice poster here that you can build this model. I won't go into great detail about building the model, but it's kind of cool. It's a cutaway view. So you see you see snow at the top. So this is the surface. Snow falls, builds up in layers. And if we cut away to where the drill is actually cutting through the ice, underneath you can see snow and then firn, F-I-R-N. Firn is snow that's been compacted, and a good model is a piece of styrofoam. It's like that. It's kind of crunchy. It's old snow basically. But then as more and more pressure, more and more layers are added, more and more weight pushing down, there's a firn to ice transition. And it's at this point when the ice, it turns to ice and it captures those bubbles that we've been talking about underneath in this cutaway view. So the ice core is dropped down. The engineer came up with this really cool core barrel. It doesn't have to be that complicated, but drop it down, and at the beginning it doesn't go down very deep. It pulls up an ice core. I'm going to tilt this so you can see it here. So it actually pulled up an ice core. The ice core has, in his version, actually has lines. He made it out of a screw. So that it's got lines on it to show the layers. But then they put the drill back down, like Mary was saying. They go deeper, and they pull up another one. And they go down again, and they keep going until they get to the depth that they want to reach. So they keep keep drilling with this. This is just, it's nice because it's just a, it's on Velcro. I can take the whole thing apart. It lays flat for me because I'm having to travel around with it. For you, it's easier to store if it lays flat. But it shows you the directions in the drill model and on the website. So just another resource that I just wanted to let you know is available. Any questions about any of those things?
It's not a magnet that
Yeah,
pulls
that
up
was
the
my
course?
question. Yeah, yeah.
I mean, like I said, this is the engineer. His has torque things on it. I mean, it's really kind of cool.
So it's a magnet, right? Like you are pulling
All
out.
I do is I have a dowel rod. I put a tack. I make little ice cores with pictures of the ice core like you have around a dowel rod with a tack stuck in the top of the dowel rod. And then a string, a magnet that goes down, pulls up the dowel rod from the tack. It's just an easier way to do it than the way he did it. But you get the idea. And the Cutaway View is the same as that. Any other
Wonderful.
questions?
Thank you.
Do you sell this do you sell it that we can order it?
You know what? I don't yet. Bill and I have been talking about this, that what we might do, I just have to get permission from NSF and from Mary at IDP. But I was thinking if we had kits put together by one of the companies, if they would be willing to, that would be a good thing to put into a kit and make it available. So if after all of this is done, if there's an interest in that kind of thing, we can go pursue that and see. I imagine we can get something like that done fairly quickly. Any other questions?
What form do we have to keep these? What form?
I'm sorry, say it again.
Do they need to be like a ball?
It's going to change shape, whatever you put it into, because it's just, you know, it's going to,
Like that? Okay.
it drips, the ball, whatever you do with it, just hang on to it either on that wax paper or in a Ziploc bag until tonight, and also have the cup. And we're going to do something with it tonight.
Okay.
We need to, yeah, if you put it inside your Ziploc bag, it won't dry out because it's made with glue. So keep it sealed up so it doesn't dry out till tonight.
Awesome.
You want to keep it longer than that for children to play with, or when you're back into your labs, you can keep it in a refrigerator for a pretty long time. I don't have an end date for it, but it lasts quite a while. So we started. So what I'm going to do is share with you a time-lapse movie that I took. How many of you have cell phones that can do a time-lapse? Anybody? A couple of you? Okay, if you can do a time-lapse, when we do these, you might want to try it. If not, you can just take a couple pictures spaced out. And what is... There it is. So I just turned my cup over, and it's short, so you want to watch it. This is a time lapse. About, I've forgotten exactly how many minutes, but I think it was about 15 minutes.
That is cool.
It is cool.
It's cool, but it seems like it's kind of screwed up.
Yeah,
Okay.
thank
I have a hypothesis.
Okay.
I have a hypothesis that the information Bob gave us before is probably completely wrong. That's my hypothesis. I don't know Bob real well, like Louise, you know, so I don't mind going out on that limb. Because I believe Bob told us that he drew that little picture of a glacier and he kind of drew the lines going. Louise, can you show yours? Yeah, look, Bob drew his like completely 180. He drew his
so
like
the middle was
going
going
faster.
faster. Yeah.
And I believe Louise just showed you evidence. I mean, claims and evidence. I'm looking at that and I say, hey, I got a claim that the middle of the glacier goes the slowest. And I got evidence, video evidence there to back it up. Now, and I got even 100% of my data that I collected. Which you look at, 100% of my data.
I'll be with you. Yeah.
shows
It's
that
awesome.
actually,
Channel.
Bob's
Yeah.
information must be wrong.
He's awesome.
It's not in a channel though.
But
You have any
I do
really
have a
wrong-
question. Hey, Louise, you did send oozeballs to all these people or glue? Every single person on the screen has one of their own, is that right?
I didn't send one to Bob, but everybody has one, yes.
Everybody else has one.
So,
And everybody has maybe a marker at home of some kind they could get their hands on?
and you've got a vis-a-vis and your land ice, sea ice that you had this morning, so you could use that. That's what I use.
Oh, and you got a surface to put their goo on where it's not gonna stick like a terry cloth towel, like the terry cloth towel, bad idea.
on the
Or like
back,
the back of a notebook?
that works great.
So
So,
what do you mean? You just prop your notebook up like on an angle or something?
yeah, let me turn on my little camera.
You know what? Hey, there's 12 of you guys. Can you guys please do an experiment to see if Bob is right or if my claim and evidence is correct to show that the middle of the glacier actually is the slowest?
Valley.
The only, you guys got a notebook. You can set it up any way you want. You got a notebook with a surface that doesn't stick and you got a wad of glacier goo. So let's
You
take.
mean ELA point?
I don't-
ELA point?
ELA point, you can make the ELA point wherever you want, Rose. All right, it's your goo ball, it's your notebook cover, and it's your marker. Can you guys design an experiment and collect some data? Maybe even take a picture or two on your camera as evidence, and in 10 minutes or so, we'll turn it over to Bob and he can either he excuse himself for the rest of the night and I'll talk about glacial dynamics, or else I'll eat crow and turn it over to Bob and
I
learn
think
about
he's
glacial
gonna take me on
dynamics.
his next, he's gonna take me on his next research expedition because it's so amazing what I've
I
done.
know he's not going to take me on it now. So
Okay, take a
While
couple
you
minutes.
guys are experimenting, let's angle the camera so we can see.
Now,
oh yeah,
Record over here, but
the experiments that are going on, that would be great.
get some pictures of yourself doing it. Try to get a time lapse if you can, or take several pictures, but post some pictures. I'll put slip sliding away on the Padlet so you can post them right there, or even take them with your computer. Bob, have you ever seen Padlet?
You know, there was a link to it, but I have not seen it yet. So I should go to that link and have a
Go to
look.
the link at the top of the agenda if you can, and you'll see where they've been posting. You're going to want to do this with your students. It's awesome. Matt, that is amazing. I love that picture. Oh my gosh.
Oh no, Padlet. I went to the Pear Deck instead. Padlet.
Yeah, go to Padlet. So there's a slip sliding away category there now.
Oh, cool. So this is like you can put in.
They
Put up
all have
little-
the same link, and all they have to do is click on the plus under any of these and post their work or their pictures, comments. So it's just kind of a record of the entire workshop this week of everything we've been doing. It's kind of cool.
That is neat.
A nice tool with your students.
Louis, what is the you gave it out, it should be somewhere, the password for peer deck?
That was just for that particular set of slides. Anytime that you sign in with that, when you have that, like if I have my Google slide open and then you do the add-on and you, there's a little, you kind of need to watch a YouTube about how to do it when you set up your own set of Google slides, or you can use my Google slides. You just have to do the add-on Pear Deck yourself, and then that generates a username, password kind of thing, or a password for that username. After the workshop's over, if you can't figure it out, let me know and I can walk you through it, or I can write up some directions and share. I won't have to do that
Thank
until
you.
it's over.
Actually, we have adapted the what is this, the Padlink? Yes.
Yeah, Padlet.
Padlet, yes. We are taking this, yeah, from next semester we'll do that with our students.
It's nice, and I really like.
Bill, I hate to tell you, I have a smiley face going on here.
Wait, what? You have evidence to refute my claim?
Actually, Billy,
It's always important to not throw data out just when it
Absolutely.
doesn't fit what you think. It's always important to figure out the reason why the data does not match what you think. Students are
Although
famous for that.
we can talk about this later, but when you look at it, those data actually match exactly what I would expect when I think about it.
Oh, yeah.
Yeah. So we'll talk about it later.
Yeah.
State it's more complicated.
Well, Bob, I'm certainly counting on you to explain the glacial dynamics here.
So this glacier glue is much more viscous than the stuff that I've made in the past. Can you tell me kind of a little bit about the recipe? Is it like Elmer's glue and borax mostly?
I mixed in this recipe, and actually Bill is the guru of making glacier glue. We actually have a video up of him making a big batch for a class, and that's a different amount, obviously. But I worked with what they had in their little packs that I sent to him. It was I think it's almost,
nice
it's a little over
recipe.
100 milliliters of glue. Elmer's glue mixed with, I think it was 75 milliliters of water. Mixed that first, and then they had a 55 milliliters of saturated borax.
Yep.
They had saturated overnight. So.
Oh, I see. Saturated it with water? It was just like regular water?
Borax. You have 55 milliliters of water, and then I had as much borax as you can. I gave them.
Cool.
And so that it precipitates out overnight, and you have a little layer in the bottom and clear on the top.
Neat.
You have a nice
Really,
saturated.
the recipe you sent out, Louise, was really nice.
Yeah, that one turned out well. I had to do it a few times to get it there, but I learned it from Bill. And there is a really nice video online that he's done that teaches how to make it in big batches.
Like 2 gallons at a time, you know?
Yeah.
5 a gallon Elmer's glue.
Yep.
We do
I
it.
told this story when I've had to mix the glue at past school vices, but I didn't make the connection that this was that guy.
Oh, I'm the goo guy. Yeah.
You're the goo guy, yes.
Everybody's got their skills, Lauren, you know? Got to know your skill set.
How are your experiments coming? Are you doing anything different? Did you draw lines? What did you do?
I just put lines on mine. It's going. It's almost eaten the 3rd line. So I got about, I think, 10 seconds worth of time
Carol,
left.
I need that. Hey, Carol, I'm going to get a screenshot. Hold on 1 second. I want you right there by your goo. Just give me a minute to get my screenshot.
Oh, that's great.
That was a great goo screenshot of Carol. One more second. I'm almost there. All right. Thank you, Carol.
Well, I started with 3 straight lines across, almost like whiskers, and now I have one happy face that's just about to disappear. So the other 2 lines have gone underneath as it spread out. So we're just left with the happy face that looks like a white sock.
So Louise, let's give it another minute or 2, and then maybe you can show your video clip again, and then we can make. This is why one thing that I think is really important when you do things with kids, when you start opening up instructions and open up ways for them to do investigations, is a lot of times it's important to look at class data, because groups of kids do make mistakes individually, but a lot of times if you look at the entire class as a whole, you don't have to go back and correct each kid. You can get them to accept the fact that, hey, we did 10 groups did the experiment, 8 of them got this result. The data suggests that this is the right result. And then if you have time, you start to go back to somebody like Louise, whose data led me to the wrong conclusion possibly, and say, okay, what did she do differently that might explain why her results don't fit what we see in the field with glaciers and what we see with most people?
Yeah, what do we want to do?
Yeah. How many people, can you guys give me a thumbs up if your data suggests that Bob knows what he's talking about?
This one.
Nice.
Rita, can you show yours again? You had it up to the camera a minute ago.
Actually, mine will support Bob because the middle is coming a little faster.
Yeah, okay. Interesting.
Yeah. Nice.
So I thought, you know, with friction, the sides will move faster. But anyway, I mean, that's a wrong assumption. So that's my aha point today. I learned it, yes.
I think the cool thing is that it doesn't slide down. It's the top rolls over the bottom at the face of this. I think that's one of the cool things that I wouldn't have realized before.
We do have one piece of data though. Louise, can you show yours one more time?
The middle is coming faster.
Yeah, I'm gonna,
Not on Louise's there, it's not.
on mine, it's not, I was shocked. It was not what I expected.
So with that, I think we're going to turn it over to Bob to talk about glacial dynamics, and he can maybe explain our discrepant event.
So I thought about this a little bit actually, and the first thought I had was what I think Matt had suggested, or no, Russ had suggested about the front end folding under, and that is one thing that we generally don't see on real glaciers. This is one of the big differences between this glacier goo and a real glacier is that the glacier goo, as I think Rose said, is not ablating at the bottom and it's not accumulating at the top. So that's a pretty significant departure. And so you get this thing where it's effectively rolling over on itself because if it's not sliding against its bed. But what I was thinking about, you know, after a few minutes of looking at Louise's video, Louise, do you think you can put it up again?
I have to get my mouse over to this.
Yeah, no worries. It is really all about the geometry. And so if you look at the beginning of the video, early on, so the question is, now pause it if you will, if you can. Actually, any place is fine. The thing to look at is the distance between the surface of the goo and the cup. Because something that's really different in my mind between this and a real glacier is you're sitting on this, this glacier is sitting on this convex hump instead of sitting on a concave U-shaped surface, right? And so one of the big differences then is you've got a lot more thickness on either side than you have right in the middle. And that's actually one of the, in a funny way, as opposed to sort of refuting the physics of the glacier velocities, it illustrates that exact thing, that where it's thicker, where there's more material between the spot that's resisting flow, you get faster movement. And in this case, because of the convexity of the cup, it happens to be on the edges.
Could you say that again?
Sure. It has to do with, so at this moment, Louise, if you paused it, and now you've seen this in 3 dimensions more than the rest of us, we're really only seeing it in the 2-dimensional, but if from the viewer's viewpoint, you poked a toothpick through the middle of the glacier, I'm gonna just go out on a limb and say, right now, right in the middle, it's thinner. Your toothpick would go less distance in than if you went on either side. And so that there's more material between the wall of the cup and the surface of the glacier on the side than there is in the middle. Do you think that's a correct characterization of the geometry?
It started out as pretty much a ball on top, and I kind of pulled a little bit of a tongue just to get it over the edge, and then put my lines up above that. So it was more like a ball sitting up on top, and it flattened out in all directions.
But this would be an example where because of the geometry of the cup, it's quite a different what's the right way to put it? It's a different set of forces on the sides of the glacier, if you will, than it would be otherwise. I feel like at least one of you guys had the cup set up where the goo was inside the cup. I can't remember which one it was. There was one with the goo.
I had it in the cup.
That was yours, Matt. And do you still have any pictures of it? Because that would be a much better example.
I'm trying to upload it. It's still processing.
Okay, cool. But yeah, this would be why, like Louise's, this tray she's got now.
Yeah, I don't know if you can see it. I can move.
No, if you pin this video, I think it looks pretty good.
You can see the black lines. I didn't do it in color, but let me just turn it sideways so you can see it's just PVC pipes and elbows, and then tees to hold the feet, and it's a rain gutter with a hole cut through in the top. That's just all it is. The directions are on the website under Slip Sliding Away.
That's
so
great.
You can hold your own.
Lauren and Layla can pin that, or they can put the link to Slip Sliding Away on your syllabus also, so you have it there. But it could be as complicated as that rain gutter, which is not real complicated, but makes for a great class set. If you invest in building it once, you have it forever with your kids. Or it could be as simple as your notebook. I mean, just with our notebook and our little bag of goo, we all got the same kind of data. So very low entry point to get your kids engaged and do those activities before the real content.
I have portable whiteboards. That's actually what you're seeing here. And I have a class set of those, that I have the students do other projects on, but the whiteboard surface is nice because it cleans up easy too.
Cool.
Yeah. I have a whiteboard also, okay.
If you do invest in Louisa's gutter system there, what's really nice is you can do additional experiments. Instead of just drawing lines across the top, you can start to put, like what Bob mentally painted there, put a toothpick in it to see how deep it is. But if you put a row of toothpicks through it, then you can start to see and gather evidence to see which part of the glacier moves the fastest, the top or the bottom. So lots of experiments. And then if you're doing math with your kids and you want to start getting some math in there, it's easy to start to calculate rates, just centimeters per minute or something like that. Just so that they start doing some math, that's very accessible math in there as well. So
I just turned mine over and Bob is correct. The outsides were much thicker than the center of it.
Cool.
Go
sorry,
figure.
Bill.
That's why Bob has a PhD and I'm known as the goo guy.
That's right.
It could be interesting to note that, like as Bill was saying, if you stick your toothpicks in and you might be able to figure out whether the top is going faster or the bottom is going faster. That's actually something that we do, not with toothpicks, but we actually I've designed some tilt sensors. You drill a hole through the glacier. It's a vertical hole to begin with, and then I install these tilt sensors in the glacier, and then you track the tilt of those sensors over time, and you can actually see that curve that I drew in the slides earlier after a certain amount of time.
So Bob, would it work if we put beads in 3 different locations and see how the beads rolls with the ice?
I think so. You could do that in the across glacier direction.
Right.
The thing that you would find difficult is if you were to set up a trough like Louise. Remember we talked in the thing before about is it going fastest at the top, at the ELA, or at the bottom?
Mm-hmm.
And that is unlikely to work with the glacier goo simply because there's no accumulation and there's no ablation. And
I see.
So that part probably won't work the way you would expect it to.
Bob, does it work if they do accumulation and keep putting more goo on the top?
That's an interesting question, and I don't know. I would guess it won't, and I'll tell you why. It's that in response to that accumulation, you do tend to get increased thickness towards the ELA, and then it's also getting thinner towards the toe because of the ablation. And so my suspicion, if you increased accumulation of goo at the top, is that you would find you'd be making it thicker, therefore it would slide, it would move faster. So I think that this is really good for showing the lateral differences in velocity, but maybe less so for those longitudinal ones. One other thing that I've seen done with this stuff is to illustrate the impact of an ice shelf. So if you took Louise's trough and you took Louise's trough and you had it coming down into onto a surface, you could build an ice shelf at that surface, and then if you remove that ice shelf, you'll see the ice coming down more quickly.
There's a great activity on in one of the Andrill resources that's on the Ice Drill website now. It's in Antarctica's Climate Secrets, where you literally have goo on a map of Antarctica, and you have foil ice shelves and remove the ice shelves and see how the ice will flow. So that you have to set up a model like that too with the map.
Another thing you can do with Louise's setup is, I don't know if you've talked about this before, but you could also lubricate the trough with some like cooking oil or something, and then you could illustrate how you're going to slide along that.
Now we've put spray Pam on it on one and then sandpaper on another.
Yeah.
Put a rock in the middle of it and see how it moves around a rock, or if it moves the rock, things like that. It's pretty cool.
Would that work if you put like sediment in it somehow? I don't know how
we did that when I did School of Ice a couple years ago. We had the sediment one, and we put a bunch of gravel down.
How do you get it to, if it's on a slope though, how do you get the sediment to stay?
We used a spray. There was some sort of adhesive, I think.
Can you glue them?
Or maybe it was maybe we had to sandpaper the trough.
I think it was sandpaper.
Maybe it was sandpaper.
Did it pick stuff up then?
No, it didn't pick it up. If you wanted to see a model that models, like, for example, sediment under an ice sheet or under a glacier, there's another one in Antarctica's Climate Secrets where you freeze water, you put sediment in the bottom of the pan, freeze water in a brownie pan, and then get a paint tray that's tilted with water in the bottom and put the ice sheet on the land's upside. And as it melts and slides down into the water, it also starts to drop sediment out the bottom of the glacier that goes into the water and goes out. That's from that's kind of that crossover between ice drilling and Andrill, because it was really for sediment cores that we were looking at how those sediments were carried off land and ended up in our sediment cores. But it's kind of a nice model. That's in Antarctica's Climate Secrets. It's on the website too, kind of down at the bottom of that list of resources. Andrill's website's down, and so Dr. David Harwood gave me permission to publish them on the ice drilling website because teachers are still using them. They're really good models.
I don't know if anybody's been watching the one that I have here. I keep adding a little bit more at the top, and it's picking up speed as it's going down. My little mountain here.
I'm thinking that is maybe due to gravity or something. It's going fast, picking up.
Yeah, picking up speed. Well, a glacier.
Yeah. Up to Brittle, it is doing good, but once it comes to down, it's very fast.
The accumulation zone is building up there.
Right.
That's pretty cool.
Cool. So you've got Bob here, and if you have any questions about glaciers, you can pick his brain or ask him how he got into science.
It's mine, it's going fast.
That's cool.
I was asking about the sediment on you know, like using it somehow to see how it creates the different features. Like I think it was Meredith that was showing us, and I try to do a little lab on it. I just I use stream tables and I throw a bunch of sand down, and then I put a bunch of snow on the sand, and I literally have the students push the snow through it just as a demo, and then behind it, it's all sorts of, you know, like eskers, and then in front of it's the terminal moraine, and it just to identify with some of the sediments that are created from the formations, the landforms that are created from that. But I was hoping that this might be used instead of snow, because sometimes snow is hard to get and messy.
Right, of course. Yeah, I think one of the...
Do you use, what you tell, did you use sediment?
Yeah, I just put a bunch of sand and
Sand,
gravel.
okay.
Do you tilt the table, Matt?
No, it's just the kids physically pushing it. It's supposed to be just helping them identify quickly with how a glacier could create landforms behind it. Because in Colorado, we don't have glaciers. We don't talk about that. You know, they don't see stuff like that at all, really. So what is a glacier quickly? It's a bunch of snow. And then what were the formations behind it? It has to do, I show it because of Alfred Wegener's evidence, continental drift and stuff like that. But I was hoping this might be a replacement for that. That might work somehow.
It'd be interesting to see what sort of landforms this stuff would leave behind. I think it would depend a little bit on how stiff it is, right?
So,
what was the
hey,
question?
Bob,
Oh, I was saying it'd be interesting to see what kinds of landforms this goo would leave behind, and I suppose it would depend a little bit on how stiff it is.
so Bob, I have a question for you about glaciers.
Yeah.
We've heard from people during this week that Antarctica slows, that there's a lag time between when Greenland slows and Antarctica warms, the warming periods. And I know that we have a lot of evidence in Greenland that the glaciers are retreating, and they can actually measure, and you can see pictures as to how many meters per year, and they're accelerating. Do we see glaciers accelerating in their melting rate, or the terminus moving back at all in Antarctica, or is that not started down there yet?
Mostly, so there's two things that we're seeing in the Antarctic, and it is interesting because, you know, only in the last 15 years or so has there become an agreement on and a ability to determine whether the Antarctic, whether the East Antarctic in particular was gaining mass or losing mass. And so have you guys talked with like Eric or Meredith perhaps about this term Clausius-Clapeyron and how much moisture air can hold? So one of the really interesting things, kind of a conundrum, I think, about a warming climate is, if any of you, like, give me a thumbs up if you've heard the expression, it's too cold to snow. A couple people have heard that, yeah. And so the main reason that you find that is that the warmer air can hold more moisture. And that's, people attribute that to this Clausius-Clapeyron relationship. But the point is that if warmer air will hold more moisture, you could imagine that in general, in a warmer climate, you would be able to create more snow on a glacier or on an ice sheet. And so, in fact, this has been hypothesized pretty frequently as this is a negative feedback on the ice sheet, on the mass balance of the ice sheet in a warming climate, because as more of it melts, you still have a warmer atmosphere, and so that can cause more snow to accumulate. Now, there's two things that I can say about that, and the first is we are seeing I'm going to go to Greenland for a second, Bill, and then we'll go to the Antarctic. One of the things we're seeing in Greenland is right in the center of the ice sheet, the elevation or the thickness is pretty stable. It's actually increasing in thickness just a tiny, tiny bit, 2 centimeters a year. But that is more than balanced in terms of the mass balance by the high thinning rates near the coast. So you're getting things a lot thinner near the coast, and things are getting a little bit thicker in the middle, or they're holding steady. One of the interesting things to think about then is that you're taking an ice sheet with a profile that looks kind of like this, and you're changing it into an ice sheet with a profile that looks more like this, because you're thinning the edges and you're either thickening or you're holding the center constant. Well, what that's done is you've just steepened the ice sheet, and you guys can do the experiment with your glacier goo. What happens? Yeah, what happens when you make it steeper? It goes faster. And even if you are able to keep this in steady state at a faster rate, at a higher flow speed, one of the things that a glaciologist might tell you is that, well, if there's faster flow, that means that the residence time of any little bit of snow in there is shorter. And that means that it has greater sensitivity to changes and perturbations in climate. And so even if you were to say, okay, well, there's more snowfall, so you're getting more up at the top and you're thinner at the bottom, not much change, but we're increasing our sensitivity. So now to the question of the Antarctic, and there's two answers, Bill. One is there's not a lot of change, and the other is yes, there's a lot of change. And the reason for the two answers is East Antarctic and West Antarctic. So I can actually show again my actually, I guess Louise would probably need to make me host again.
I thought I did.
Which one is melting faster, eastern or the western side?
Western, yeah. So I'll just sort of show you a little bit about what's going on and how it changes. That one, this one. All right. So this is the East and West Antarctica that I showed you guys before. And so what I failed to tell you, or failed to state clearly, was that you've got the Transantarctic Mountains coming across here. This entire side, the East Antarctic, sits at a very, very much higher elevation and is grounded much higher than the West Antarctic. So the East Antarctic is referred to as the polar plateau, and this East Antarctic polar plateau is sitting at about an average of about 3,000 meters above sea level. So that's very, very high, and it's very, very dry. So there's very, very little accumulation. In fact, it is technically a desert, in spite of the fact that there's kilometers of ice under your feet. It's a desert. In contrast, the West Antarctic is maybe averaging closer to about 1,000 meters or 1,500 meters above sea level. So it's in a much more warm climate to begin with. More importantly than that, the West Antarctic ice sheet is, most of it, grounded below sea level. Have you talked about grounding below sea level so far?
Mm-hmm.
A little bit.
A little
Okay.
tiny.
Yeah. So here's a diagram of what that kind of thing looks like. Is here's sea level here, and as the ice flows from the grounded area down over, so this area here is floating ice. So that would be what's called shelf ice, and so that's the kind of ice that you see. Well, we saw that in the ice shelves, and as I mentioned before, that ice is floating, and that means it's floating. It's already displacing its entire mass worth of seawater. So it's technically not contributing to sea level rise. And so, for example, little pieces can break off. That actually happens all the time in the Antarctic. You'll see giant icebergs in the news. An iceberg the size of Manhattan just broke off the Antarctic. But that's not surprising. What we worry about is when this grounding line here starts to retreat backwards in towards the interior, because one of the things you can see is that once this area has no contact with the bed, it accelerates because it no longer the bed doesn't have any pushing back force on it, and when it accelerates, just like, okay, get my second thing of silly putty. When it accelerates, so let's say my right side is the side that's on over water, and the left side is on land. When it accelerates, it stretches out, and when it stretches out, it causes it to thin. Well, when it thins, it becomes more likely to go afloat. And so this is what causes this it's called the marine ice sheet instability. So it's a feedback. And so that's something that, that's really why people are concerned about the Thwaites area, and why people are looking very, very carefully at this grounding line there. Does that make sense? I don't know actually if that really answers your question, Bill, but it was maybe an attempt at it.
No, yeah, no, it does. So do you see the more accumulation above West Antarctic ice sheet too, on top of that ice sheet? Is there more accumulation at the center of that?
So yes, the short answer is yes. There's a couple of reasons for it. One is that in the East Antarctic, it's this gigantic continental-sized piece of ice, and so most of the air masses that have come up onto the continent have done their rising by the time they get, I don't know, within a few hundred kilometers of the coast. And so in the interior, I'll step back for a second and do the basic meteorology. You take an air mass, it's got a certain amount of moisture, you push it up in the atmosphere, and that cools it. It means it can't hold as much moisture, and so precipitates out. And so oftentimes that's done by pushing the air mass up over a mountain. It's called orographic lifting. If this is all obvious to you, just let me know. But in the East Antarctic, most of the interior is quite flat, so there's not a lot of extra elevation for the air masses to gain, and therefore it's not as likely to precipitate out. So yeah, so you tend to.
Wouldn't the air be pretty dry anyway, because it's to get up to 10,000 feet, you've squeezed it all out at the coast?
Right. Yeah, exactly. And so with it higher and flatter, first you're starting out with very dry air, and then you're not actually doing much lifting in the process.
I never thought of it that way. Yeah.
Yeah. And so yes, in the West, you get a lot more.
Well, when you're talking about, snowfalls, I mean, I know like the dry valleys get nothing. So from a minimum of 0, what's a maximum down, in the lower elevation?
So you can get, it's highly variable. I mean, the one thing to remember when we talk about the Antarctic and the climate of the Antarctic is the Antarctic is like North America in terms of its scale. And so the panhandle of Texas is quite different from Alberta. But I guess one way of putting it is at South Pole, right in the South Pole, which is not really in the center of the East Antarctic, you get an average accumulation of about 9 centimeters per year of ice equivalent. And so that's ice equivalent at density of 0.9 or 917. If it falls as snow, that's more like 30 centimeters a year of snow. And so that's like this much snow a year. I mean, that's not very, very much. Contrast that with some of the places closer to the coast. There are several meters of snow a year. The challenge that, like I said, it's difficult to generalize from the physics of it because there are so many different pieces to it. And you get weather patterns, storm systems that come in off of this particular sea and pop up against that spot. But yeah, you do definitely get places where you get multiple meters of snow.
I have 2 questions, Bob. In your first or second slide, you said that glaciers were elastic, and then the next sentence you said they're brittle. That to me seems like opposite.
What's the deal here? Yeah.
Yeah.
Great question. And the answer is that they are. But it differs depending on how that stress is applied. So the elastic versus viscous versus brittle is the response to stress. So if you take ice and you apply a very fast stress, but over a very short strain, meaning you don't push it very far, but you push it really quickly, the ice behaves inelastically. And so there's two ways of illustrating that. One is, and it's kind of a hard sell to tell you that ice cubes bounce, but if you drop an ice cube on the floor, you will be able to see some bouncing action. The other way to sort of illustrate that is that you can take and do a seismic sounding. One of the earliest ways of determining the thickness of the ice sheet was to set off explosives at the surface and listen to the seismic wave that reflected off of the bed. And so the only way a seismic wave like that can be transmitted is because there was some compression that then relaxed. And so that's what an elastic rheology is. It compresses and then it comes back. It's all recoverable. So then the question is, okay, well, what about the brittle? And you can illustrate the brittle fracture also by dropping an ice cube. And that is also a fast strain, but it is a higher magnitude of strain. So if you push it really fast, but only a little, then you can get it to behave elastically. If you push it really fast, but push it a lot, then it'll behave brittly.
Can't we do that with the goo too? Like if we pull it?
Oh yeah, yeah, you can break the goo. Absolutely.
It bounces, and if you hold it up, it's gonna.
It'll do the viscous thing. Yeah, yeah.
Here's something I wanted to bring up about my glacier over here. Is I was feeding it at the top a little at a time, and I started to notice that the top, as I was adding to it at the top, it was moving faster than what was on the bottom, and I wound up with curves as it went down. So I would think that the lower layer is moving much slower because of the friction than the top accumulation. Now, what I'd be interested to try to do was the same thing, except use different colored goo and put it on there to see how it would deform and see if it would move. Because it's clear to me that it's there. You know, you can see it, that it is not straight, it's definitely curved.
Yep.
Yeah, you can add food coloring when you do the water and the glue. That's when you add food coloring.
I'm pretty sure we did that at our iteration.
Yeah, we did.
Where we had the different layers of the different colors. It was really illustrative, and then the students really enjoy the colors.
A question about the Antarctic mountains. Like, first, do you know how they form tectonically, or how old they are, and then do they impact climate, or do the mountain glaciers there have much impact on the ice sheet behavior?
Yeah, absolutely. I'm going to share this again to go back to that map. Geologically, I don't actually know how they formed geologically. I believe that they are, well, they're of tectonic origin, but I actually don't know a lot about the geology underlying the ice sheet. Although it's pretty heavily studied, so there are lots of people that go up into the Transantarctics to try and understand the tectonic regime. But they do have a pretty big impact on the ice sheet dynamics. In particular, I'm going to just illustrate. So the dark colors you see here illustrate kind of, these are flow divides. So you can kind of see where ice is going from any given place. And so one of the things that you can kind of see is that these Transantarctic mountains, if they weren't there, you would see a lot more flow going a lot faster down into the Ross ice shelf from that side. And so one of the ways of thinking about it, I actually have a picture of the Transantarctics back up in the types of glaciers section. There we go. So this is we're flying over the Transantarctic mountains. And so you can kind of see that the ice is flowing down in between the mountains, which are just stuck up out. And so they provide a really big, they're quite influential in terms of that flow regime.
Thank you.
Yeah. Are there parts of of your question that I didn't get to? I couldn't quite remember exactly all of it.
Do the mountains extend to the coast, and are they big enough to like impact the wind patterns and where there's more snowfall on one side than the other? Does that happen?
You know, I don't know. I think that they do extend out towards the coast. In fact, actually, I think that they're right along in here, and there's a pretty big pretty big and distinct. Yeah, they do impact wind patterns because you get this channelized winds that come across the ice shelf. The ice shelf is super flat, and then you get the wind kind of tunneling up through these valleys up onto the polar plateau. An interesting side note, this is how the early explorers in 1910, 1911, that's how they were getting to the South Pole, is they had to get through the Transantarctic Mountains, and so their general route, they started right in this area, and they marched across the ice shelf, which was totally flat for a while, and then they headed up one of these outlet glaciers to try to get to the pole. Quite interesting.
Is there a difference in the impact between the two different types of movements of glacier, like the sliding and the slip?
Yeah, I think it's safe to say that definitely yes. And here's a good illustration of that. So this is these are what's referred to as the Disciple Coast ice streams. So here's Antarctica here in the corner, and we're just in this box. So this is that Ross ice shelf. The route up to the South Pole that the explorers took was kind of this way that I just showed. And so this is illustrating the flow speed of these ice streams, which are, they are, a way to think of them as rivers of ice within the ice sheet. So the edges of these ice streams, you know, you can pretty clearly delineate the edges of these ice streams, right? But that's not because there are any river banks. There are no river banks on the surface. These areas between the ice streams are also ice. And so what we're pretty confident of is that what's going on is there's a lot of sliding because of the conditions of the bed in these ice streams. And so what's the difference between the fast flowing ice streams and the slower flowing area in between is that sliding. So I think that I would say sliding is probably the much more important factor in most of these cases.
Bob, could I ask you a question on a kind of a different direction here?
Totally.
There's all of these people work at minority serving institutions.
Mm-hmm.
And with all the news right now and increased emphasis on equity across the entire world, can you talk a little bit about glaciers and say, for example, the Himalaya or tropical regions that are used for people's water supply? And, you know, when we start talking about climate migration and things like that, can you talk about the impacts that you see coming when we talk in terms of equity across the planet?
Sure. And I mean, I think one of the simplest ways to put it is that those who cannot afford either monetarily or for other resource reasons to move away from the places that are impacted by things like sea level rise are the ones who are going to be suffering an outsized challenge from this. I mean, that's probably the most fundamental is, you know, if you don't have the resources to escape either from either the resources in terms of how much space you have to work with or the resources in terms of money to just leave, that causes you trouble. Turning to places like the Himalaya or other places, yeah, there's a huge amount of water resource issues associated with melting glaciers in the Himalaya. And that's one of these, the challenge of that is that those are the impact on the Himalayas, and in terms of the water, as far as I know, I've dabbled a little bit in Himalayan glaciology, but not too much. But the impacts on those water resources are not as clear at the present. So we can say, hey, look, the mass balance of this glacier is negative. It's not in balance, and so if if you're relying on this as a reservoir, you got to know it's going to disappear. But like so many things in the problems of climate, the change is very slow. And we think, okay, well, it's probably going to be gone in a couple of hundred years. And so it's very hard for civilizations to think that far in advance.
Bob, a question on your blog. I was just looking at your webpage. You mentioned some of the work you're doing with UAVs. I'm curious how that technology, how do you see that changing things? Where is it going? What cool things are you going to publish here in the next couple of years that we're going to get first glimpses of?
Can you define UAVs or UAVs or what?
Sure. So I would refer to a UAV as an uninhabited or unpiloted aerial vehicle. I personally have a small fixed wing UAV. It's about a 2-meter wingspan. And by comparison with most UAVs or drones, as they're referred to, most people will have like a quadcopter. The biggest challenge with any of these instruments, especially for a glaciologist, is the range and the ability to actually cover ground. So for me, in most of my work is much larger scale than a normal UAV would cover. What I have been able to do with my UAV, I guess I got time, I can show you this. Let me see if I can find it. Is I've been able to use a technology called structure from motion, which allows you to use aerial views to generate a digital elevation model. And so I've actually, it's an interesting study. Hang on, let me just pull up. Share it here. And so this actually comes to a different piece of what I do, which is I'm involved in some management of the big ice sheet station in the middle of Greenland, a place called Summit Station. And so we wanted to, one of the things that's happening at Summit is the structures. This is in the middle of the Greenland ice sheet, and the structures that are placed on the snow there, because you get roughly 65 centimeters of year snow equivalent accumulation each year, as that snow piles up, the buildings are sinking down. But even as they're sinking down, they're also becoming drifted with snow each year. And so what I set out to do was to try and illustrate to the decision makers at the National Science Foundation that the extra money you pay for putting a building up on stilts, which allows the snow to drift underneath it and not pile up next to the snow, next to the structure, was worth it, because if you let the snow pile up against the building, you're going to end up having to pay money to have a bulldozer take the snow away. And so what I did, this is the UAV that we launched, and we flew a sortie, a mission basically, right around Summit Station. And so this is an example. I'm realizing this is probably small on your screens. How big is it? Do you know, Louise, if there's a way, if I make it bigger on my screen, will it become bigger?
On our screens, you can go up to view options next to where you're seeing your viewing Bob Holly's screen.
Mm-hmm.
I think it's 300% on our own screens.
Or I can also make it bigger too, can't I?
Too, I think.
Yeah. So here's the UAV. This is my student Joanna, who's running the computer to actually pilot the UAV. But this is the kind of thing that we were able to do. And actually, I can send you guys links to this. This is a 3D perspective view of one of these buildings. You can kind of see that it's buried almost up to the rooftop, and they've dug trenches towards the doors to be able to access the building. And the problem is that they it's a lot less expensive to put a building on the snow instead of on stilts, but it also costs money to operate the heavy equipment that they need to push the snow out of the way. So these are the different structures, right? The one I just showed you was this one here. And what I'm going to show you is next is a cross section. This is actually built on a berm, meaning they pushed snow. Let's see, sorry. There we go. They pushed snow. This is that same building. They pushed snow up into a mountain and then put the structure on top of it. But even so, it's still actually drifting in. And so this is a digital elevation model. You can see we're at a higher elevation here. We're kind of on a hill slope. I have to say the slope is extraordinarily small. But then there's a mound that the building is on. And so if you cut a section through it from Z to Z prime here, that cross section looks like this. So they built up this mound to put the building on. And this is, I should point out that this aspect ratio is all out of whack, just to illustrate it. This is the building, and then this is how much drift has accumulated over, I think it was about a year. And so one of the things that I did with the UAV was to be able to calculate the volume of this drift, and therefore from that volume I was able to calculate just how long it would take to push all of that snow away using a bulldozer, and we know how much it costs to operate the bulldozer per hour. And so I can actually quantify how much more money this costs to maintain than it costs you to build the building on stilts. Sort of the last little piece of it is this whole station, that's been happening for years and years and years, and so because of that, there's actually a bulge of the entire station. This is the general slope of the ice sheet, and make this bigger. This is the general slope of the ice sheet here, the background slope. And over the course of the last 20 years, there's been a couple of meters of extra snow built up just because of all the drifting around the building. That was actually a really long answer about UAVs.
If you want to send me the link or the article or upload it to your presentation folder, we can link their either way you want.
I can even
I
send a file.
I have another quick question, maybe quick. Is there geothermal activity underneath some of the glacial ice? And if so, where?
So you see a lot of that in Iceland. It's a really big deal in Iceland. There is, hang on, I'm trying to multitask here. So I'm going to give you, I'm going to chat this paper here. So it should be coming over the chat now, that paper. So there's quite a lot of geothermal activity in Iceland, and it does erupt up under the ice sheets, and that results in this very, very weird circumstance where you get ice melting down into the caldera of an erupting volcano. And in some cases, you get the situation where you've got ice all the way around and you've got lava inside, which is kind of crazy. But one of the things it results in is a lot of melting under the ice sheet, which I guess is obvious, and that results in these glacial outburst floods. Those are now so tightly tied to Iceland that the name for them is Icelandic. They're called a jökull, which would be a good one to get your students to try to pronounce.
Is there any volcano under Antarctic ice sheet?
There is a rift. There's a tectonic rifting zone underneath the West Antarctic. It's really hard to know exactly how warm it is down there, because if you think about the thickness of the ice, it's almost like a blanket. And so determining how much, the way we think about these geothermal zones is how much heat flux is coming out, like how much energy is coming out.
Mm-hmm.
And in order to really measure that, we have to get down really close to the bed and measure the thermal gradient, and that'll tell us that geothermal flux. And as I'm sure you've seen in various other ice drilling discussions, the number of holes that get all the way to the bed are pretty small. Pretty much every single hole that is drilled all the way to the bed, we do measure temperatures in so that we can try and determine that geothermal flux, because that's a pretty big unknown.
So the melting is now accounted for the global warming?
Can you kind of state that?
Yeah, I say the melting is related to global warming or the geothermal heat, or of the combination of both?
You know, it's almost certainly more related to the warming rather than geothermal flux. One of the big things that we're seeing is that the increase in ocean temperatures, because of those spaces, especially in the West Antarctic, where you've got ocean water coming up into contact with grounded ice, that's a really, really good way to melt ice. And so you don't have to warm the ocean very much in order to melt the ice much more quickly.
You know, just a little fact is that the southernmost active volcano in the world is on Ross Island, which is where McMurdo Base is, McMurdo Station. And this is a crystal out of Mount Erebus. It's called Mount Erebus.
Yeah.
And it's a very definite shape to the crystal, but this is a crystal from that.
I take it it's not like Hawaii, Louise. You don't have to worry about that. I saw the Brady Bunch. I know what happens if you take pieces of Hawaii, but
Well, I worked for a geological group, and I had a certificate that said I could bring rocks out of Antarctica. So I actually have some Antarctic rocks here.
Wow.
Kind of cool. I have a Vintifact somewhere, but it's not. We're not right here. But
I have a question. Maybe Louise, you might know more than Bob, but it's for either of you or both of you.
Got it.
Like I live in Hawaii, so we have trade winds here, and you guys have the westerlies. What's the predominant winds pattern? I mean, what? Because I hear it's really windy on Antarctica, but I'm not sure. Is there a certain way it goes, or does it go any way, or?
Bob, you can take that. You're nodding your head.
Okay.
You're Katabatic.
Yeah, well,
I think so.
yeah, I was go Katabatic. So the biggest winds generally see are Katabatic winds. Is that heard before?
I think you froze,
I'm seeing
Bob.
but okay. I'm gonna move around so that we'll see if you see me. Okay, cool. So the biggest winds you'll see are probably Katabatic winds, and this is quite different from something like the westerlies or the trade wind that you'll see. Those are winds that are fundamentally come from Hadley cell circulation that is set up by the global imbalance in radiative transfer, right, between the equator and the poles. The real windiness you get in the Antarctic is Katabatic, which is a wind which is essentially a gravity wind flow. So high on the ice sheet, you get some air mass that starts to cool. And when that air mass cools, it becomes denser. As it becomes denser, it wants to flow downhill. It's just like it sinks down onto the surface. And the thing about the Antarctic and the ice sheet is that there's not a lot of barriers to that flow. And so as it continues going downhill, it's increasing its density, it's coming downhill faster, and it keeps going. And so that's a Katabatic wind. So generally, if you see this, if you feel this wind coming from upslope, you're going to see this Katabatic wind.
Okay.
I experienced one of those in a tent. It wasn't fun.
Yeah, it could be incredible. But I mean, then of course you also have I would call them run-of-the-mill storm systems. The same kinds of storms you get in North America that you get in Hawaii. You know, there are on top of the sort of generalized flow patterns, you get storm systems and they rotate. So you could get winds from any direction.
So I was watching a NOAA, similar to a Zoom presentation about hurricanes. And it said that hurricanes is a way for the atmosphere to displace some of the heat from the equator up toward the poles. So does that mean, like with I think last year we had quite a few hurricanes. The more hurricanes, the more heat's going to go up and increase the global warming and ice shelf melting.
Yeah, I mean, I don't know the exact sort of reasoning of that statement from NOAA, but in general, the imbalance of equator to pole heat is a significant result, or rather, a significant result of that is you increase that amount of, if you increase that imbalance, you increase the amount of driving force to move air masses towards the poles. And once you put that air in motion, that's when you start getting those kinds of instabilities. And I guess the reasoning that I have heard for increased frequency of hurricanes in a warming climate is you get increased ocean temperatures. Those higher ocean temperatures lead to increased evaporation off of the oceans, and that in turn tends to intensify these storm systems.
Well, they're calling this year a neutral El Nino. So.
Yeah, we're in the kind of, in terms of these kinds of questions, this is the sort of thing where I know a good amount, but really possibly only enough to be dangerous. And I teach and work with Eric Osterberg an awful lot, and he knows so much more about this than I do. And so I usually like to be able to say, oh, that's Eric, talk to Eric about that.
So Bob, I finished my experiment with the beads. I used the beads, and the middle moves. You see the middle?
Oh yeah.
Middle moves a lot faster.
Nice.
Sorry.
Hey, that's great.
Right.
If you can post that to the Padlet, that's awesome.
Sure. The beginning and ending, right? At the beginning, they were all lined up, and at the end, the middle one moved. Yeah.
That's great. And you know, that's actually one of the earliest uses of, that's one of the earliest ways people used of trying to determine those things, was put a row of stones out and come back later and see where they are relative to one another.
Huh.
I can actually tie that back to Jim in Hawaii, because up on Mauna Loa, there's quite a few paraglacial landscapes and with some frozen ground. And one of my professors, Bernard Halle from the University of Washington, was doing some research there and asked me, after I was coming back from the Antarctic, as I stopped through Hawaii, to go up to Mauna Loa and take photographs of the stones that he had placed in a row, so that he could see what was their configuration.
In hydrology, we use the fruits a lot, apple or oranges for the flow and those kind of things.
Cool.
Bob, was your UAV drone, or not drone, whatever you called it, UAV, that was it highlighted in the Continent 7 series?
I don't think so.
I saw something about a UAV that it looked just like the one you posted.
Is that right? Okay. It is. I mean, the one I have is by a company from the UK called Quest. And so, you know, they're a relatively small company, but it wouldn't surprise me if they had something more high profile. So one of the stories that I always like to tell anytime I get a group of people who see students who are trying to figure out what they're wanting to do, I always like to tell the story of my own entry into academia. I more like to tell this to parents of teenagers, honestly, but you guys are close enough, I think. When I finished high school, it would be a nice, easy thing to say that I always knew I wanted to be a glaciologist, but that's completely false. In high school, I was big into music, and I thought I wanted to be a rock star. It was garage bands, and my senior year of high school, I was a middle achieving student at a very high achieving high school, and so just as I was finishing high school, I swore that I would never go to college. And so all of my friends and classmates went off to college, and I stuck around my hometown and worked dead-end jobs for about 4 years. At which point I said, you know, these jobs are actually all dead-end jobs, and I don't think I could see myself retiring from them. So I went off to college. And so as a non-traditional college student, I cast around to all the different natural sciences majors because I knew that I had some interest in science. And each one of them, I would take their intro course and I would say, that's my major. I'm going to be that major. So I was going to be an oceanography major. And then I was going to be an atmospheric sciences major. And then I was going to be a geography major. And then I was going to be, what was it next? Environmental studies major. Finally, I saw geology. I'm going to be a geology major. And then I thought, really, I know that's what I want to do, but I need to do something further just in case. So I went it's always, you need to do the opposite experiment. So I took forestry. I still wanted to be a geology major, so I came back to geology. About 2/3 of the way through my geology major, I was like, okay, I've done college. This is fine, but you'll never get me going to grad school. That's just never going to happen. And around that same time, I met another undergraduate geology major who told me that he was going to the Antarctic the next year. And I sort of like went, what? How do you do that? And he explained that it was through a program called Research Experience for Undergraduates, which is an NSF-funded program through which, in this particular configuration of the program, researchers who are funded to do work in the Antarctic were able to hire an undergraduate student assistant to come with them. Basically, they would get a supplement to their grant to pay for this undergraduate student. I thought this was absolutely fabulous. And so the guy said to me, well, and they had to take me because I was the only guy that applied. And so I thought, I'm absolutely going to try to do this next year because that's an opportunity not to be missed. So I applied the next year, and they didn't take me. And so I was like, well, that sucks. And so I sought out this professor's PhD student and said, hey, look, I want to work for you and learn more about glaciers so that the next time I'll definitely be the right candidate. And so for that whole year, I was still taking classes, and so I worked for this PhD student basically doing data analysis for him. And so the following year, he took me to the Antarctic. The professor did take me. And so that took, a good chunk of time out of my, I guess it's hard to determine what's junior year versus other years for me in college because I took so much time off. But it took a good chunk out of that year of school. So I got to spend 6 weeks at a 4-person field camp on the East Antarctic Polar Plateau, which was a completely mind-bending and, as it turned out, life-changing experience because when I came back from that, one of the other 3 people that was in the camp called me up a few months later and said, hey, I'm going to the middle of Greenland this summer and I need a field assistant. Do you want to go? Of course, I said, absolutely. I was still not at all sure that what I wanted to do was be a scientist. But so I went to Greenland, and at the summit of Greenland, there's this big station and lots of other people. And so one result of that was that 6 months later, one of the people that I had met at Summit called me up and said, hey, we're putting together a team to spend the winter at Summit, and I think you should be part of it. And I said, absolutely, sign me up. But at that point, I finally said, oh, wait, hang on, let me just try to graduate from college first, and then I'll come and do it. And so, but at that time, and so this kind of, it was a lot of wandering. And at that point, I was still not really sure of what I wanted to do. But I knew that what it was I was doing was a lot of fun. And I came home from 11 months in the middle of the Greenland ice sheet, really excited about being on ice because I was really enjoying it. And so I went back to the professor who had taken me to the Antarctic the first time and said, I want to do more of this work for you. So just hire me to be your field assistant. And he said, well, I could do that, but it would be a lot simpler if you were my PhD student. And I was kind of like, okay, why don't I try that? And so by that point, I started graduate school, and I knew better than to say I was never going to become a professor. But I still assumed that that would never happen, because this was, I started in grad school around 2000, and global climate change existed then, but it wasn't the hot topic it is now. And there were just no jobs for glaciologists anywhere. And so I kind of assumed that there would never actually be a job for me. But as luck would have it, the job market in glaciology actually came about, and I then just sort of took the jobs that came up, and here I am. So what is it? It's 30 some odd years after having finished high school saying there's no way I'm ever going to go to college. And tomorrow I become department chair. Oh, great.
Oh, congratulations. Baby, you're going to be busy.
So, you know, one of
Department chair. What a year to become department chair.
Yeah, no kidding. We also just learned that our budget's going to be contracting by like 60% or something like that.
we didn't have a volunteer, so we had to get somebody, the administrator, to assign us a department chair in our department. Yeah, nobody volunteer. We have a new chair too. One of the things I wanted to mention to you, since you actually talk about how climate change and is most recent in the last couple of decades. When I did my master's degree at University of Maine, I work on ocean acidification and impact on lobsters, you know, and they call it acid-base buffering capacity. Like it was like completely different title, but all I did was like relate to ocean acidification.
Right.
So it was really funny how it affects the organism, especially lobster population.
Right.
For the Lobster Institute. And later on, I read articles and they all have title on climate change, ocean acidification. And I'm like, oh, I already did the same thing, like 1994. And I said, it was just different title.
Right.
Now you can get lots of money for that, Rose. You can get funding.
I know, right?
One of the cool things that the University of Hawaii is doing is they're experimenting with corals, and they're finding that some of them actually thrive in the acid-based environment. And so they're going to try to grow those and replant those on the reefs that are dying out across the world. They call it Coconut Island. I don't know if you've ever been over there, Bob.
No, I haven't.
Marine laboratory. It's a whole island. It's just a laboratory setup. It's pretty awesome. My son's school went over there, so I played hooky one day and went on the field trip with them. But it's really a neat idea because the reefs around the world are dying out, and so it's a way for people to, I know they're doing it in Tahiti and some other older island chains, that they're actually growing new corals that are liking this more acidic environment, and then they're planting them onto the reefs that have dying coral.
That's very cool. Because Barrier Reef has this problem of, ocean acidity, you know, because of all the ecotourism and bleaching that's going on. Okay, all right, that's good. And where is this experiment going on?
On Oahu.
Okay.
Yeah, University of Hawaii.
Okay.
I think we're going to have to wrap it up. We just want to thank you so much for just kind of chatting with us and spending the little of your evening with us. Thank you. Awesome.
Thank you. It's great to be here. And one of the things I thought I would extend is that, especially with Zoom now, I'm more than happy to come to any of your classrooms on Zoom to talk about glaciers, ice sheets, climate, whatever. Just get in touch. Louise knows how to get in touch with me. And like I said, I love talking about this stuff.
I think you're going to have some people contacting you.
Sounds good. No, I like it.
Thank you. So Bill is going to do our reflection.
Yeah, thank you very much, Bob. Again, that was fantastic.
Cool. I think I'll go ahead and sign off then. Does that sound all right?
Well, yeah, you can just stick around too, you can sign off. We won't get offended too.
Great
art
skill.
When you do go back into the field, we might be contacting you about possibly doing a field lab experience with us with a GoPro. Send you down with a GoPro 360, and you'll have to. Well, I'll send you the link to what Eric and Meredith have done with Bill. They're really nice, and they'd be great teaching tools for, especially during virtual teaching. They'll be a really nice teaching tool. But you're just a great communicator, and you'd be able to do it really well.
Awesome. Okay.
Bob, I've got notes on my table here already to contact you, so you'll be hearing from me.
Okay. Great.
Knows the chorus. Now I'm not sure if you guys can sing the rest of the song, but you guys all know that part of the chorus because that's the most important part. So when we do this summarize the most important thing, it is like a song and the chorus because it's going to start and end with that chorus. Here is what I would like you to write in your notebooks. The most important thing about teaching climate change is and you're going to need to finish that sentence. Now, I know that just like a song, there's multiple verses in between, and sometimes it's really hard to pick just one thing that's the most important thing. So you can go ahead and put a few more things, and it's also important to do this, and it's also important to do this, and it's also important to do this. No more than 4 things, and it's also important. But then it's really important at the end, you come back and you put, but the most important thing about teaching climate change is, and you finish with the exact same sentence. So kind of like a song, kind of like a poem, we're going to start and we're going to end with the same refrain. You can put a few other things that you've thought about during this last few days about what's also really important to include. But we want to know in your mind where you're at right now. When you go back and you think about teaching these kids climate change, what do you think the most important thing is as you enter back into the classrooms? So again, write your thoughts in your notebooks, and then we'd like to share it on Padlet. Instead of pictures, I would appreciate if you would type it in. You can hang around. We'll all be here. And in about 10 minutes or so, Pramita is going to talk about her project.
Where do we put this, Bill?
Can you go over this one more time, like the most important? Yeah.
Yep. So you're going to write that right in your notebook, and then when you're done, I would like you to type it into Padlet as well, just so I can see that, and then we can process that information a little bit easier if you type it in instead of taking a picture of your notebook. But go ahead and take, you know,
It will be like a song. I have to make it like a song, or?
Oh no, this is the exact format that I would like you to use. So just in your notebook, write the most important thing about teaching climate change is, and Rose, just finish that sentence with whatever you think the most important thing is. Then you can put another paragraph. You can say it's also important to do these things because it's, you know, maybe you're having a hard time choosing. So there's the things that you really had a hard time choosing from. But at the bottom of the page, reinforce in your own mind and for us. But the most important thing about teaching climate change is boom. And you just restate. So that the beginning and the end should be exactly the same.
Okay.
Kind of like a song where the chorus repeats, exactly the same, beginning and the end.
Okay. Thank you.
Mm-hmm.
All right, I'm going to sign off, guys. It's been great talking to you guys.
Bob, thanks again for all the time today.
All right, you bet. It's been good. Talk to you later.
Thank you.
Thank you.
Like I said, Louise and I will be around for a while, and I think Paramita is going to take over in about 5 or 10 minutes and talk to us about her backpack project.
So Bill,
Yes.
I already uploaded the 3 phases of my slip sliding away.
Nice, nice. You're gonna see those probably tomorrow. In a
All
different
right.
Those pictures you guys have been putting up have been great. I think Karen has control on her Apple Watch, we found out. Yeah. I saw the little, like, the side with the finger on the watch. Yeah. Louise pointed that out. I wouldn't have noticed it. And I'm like, oh, that's how it's happening.
I never think of that. I go, oh, my watch would have done that.
I had to have my kids show me that, but that's okay.
I've done that quite a bit. I really encourage my kids to use their phones in lab and take pictures of their experiments to put into their reports and things like that, little movies and things. They have a lot of fun with that.
I was going to show you a drill bit that this is the size of the large ice cores from the disc drill. I found it on my shelf a little while ago, and I thought you guys would probably like to see it. It goes down and it turns, and it's got blades, really sharp blades, 3 blades, and it turns. The Andrill drill bits were like that too, except they were diamond blades to cut through rock. These are just sharp blades.
Louise's house is filled with different kinds of trinkets than most people. Most of her neighbors that come over to,
weird
Chardonnay with her at night and stuff like that, they don't have drill bits on there as cameos.
I definitely have weird stuff in my house.
Are we good with that, or does anybody need it still up on the screen?
Just so you know, Bob's article, his bio, and his presentation are now linked to your agenda. The agenda is growing.
So, Louis, is this Padlet will be available to us after or just during the workshop?
Bill, I think I can just leave it up.
Padlet will be there, I don't see any reason to take it down, so it just is there indefinitely.
I think as long as I have my little, free account, I think it stays up there. Because Bill has one that's been up for quite a while, I think.
A couple of years, yeah.
Well, there are some resources that we, just to check out, when we have time after this workshop.
I'll be up there for a while. If I would recommend you go through and look at it and copy and paste things out of there just in case. And I will also try to maybe gather things up and get them on the website as much as I can. I'm not sure. Bill's been taking things off the Padlet. I haven't done that, so I don't even know how.
I haven't been removing things. I've been using some of the things that you guys have posted.
Copying them or something down. Can you download them or copy them?
Yeah,
or what?
you can download them, or just screenshot them or download them.
Hope for a better internet connection tomorrow. I don't know what was going on today. Crazy. Dr. Phillip. Welcome.
How you doing?
Good. How are you?
Fine, thank you, Louise. Good to see you again.
Good to see you. It's nice of you to join.
Absolutely. I wouldn't have it any other way.
Well, thanks for recommending Paramita to take this School of Ice with us. It's great to have her.
I recommend a lot of people to you. I recommended somebody like a couple of years ago also. It's a good opportunity. It's an excellent opportunity to learn about climate change from the ice side, So and Paramita is very excited. Every day she tells me new stuff. She's quite excited to be there.
Yeah, it's changed a lot. Well, this obviously is a big change. This wasn't.
For everybody, yes, it is, yes. But I see you doing a good job of managing. I saw the outlines that you've done, and you've adapted very well. So that's great Great job, Luis.
Thank you. Every minute we are utilizing. Every minute we are learning new stuff.
Same thing online. When I was in Colorado and Lakewood, it was the same thing. Every minute was an activity. Yeah. Luis is she's very tough. But when you finish, you learn a lot of stuff from her, you know.
Okay, got the schedule. We got to get moving.
Yes, absolutely. So, Paramita, what are you guys talking about? The climate change?
Yeah, actually, we're interested to know about the sensors. I have it here.
Oh, the back. Okay, the sensors.
The backpack, yeah.
Okay. So those sensors are actually, it was adapted from chemistry class. It's Vernier. The manufacturer is called Vernier, and they make sensors for. You can buy you have a. Let me see 1 second. These are the loggers, the data loggers, and you can plug in sensors, and you can plug sensors into these to measure carbon dioxide, temperature, humidity, or you can do water stuff if you want to measure water quality. You have calcium, nitrates, ammonia, dissolved oxygen. So this is quite adaptable to any kind of classes and regular chemistry classes or earth science classes.
What is that called again, Dr. Phillips?
Vernier. The manufacturer is Vernier. V-E-R-N-I-E-R, Vernier. And this is used in a lot in chemistry classes, but we can have adapted it to, to backpack weather sensors to walk around with the carbon dioxide, methane, carbon dioxide, humidity, temperature sensors, and UV sensors, just to track local movements, from one block to the next. So we did this in New York City back in maybe 8 years ago, and we found substantial changes in temperature from one block to the next in the summertime. So there's a lot of local, the road conditions could be, if you have a paved road, or you have a grassy road, you have a grass covered area, you have quite a big difference in terms of temperature, humidity, those local conditions. So we use it quite heavily when we travel to Spain, Australia, to India, to do local micro scale measurements of climate and these climate parameters. And in fact, we use in Australia back in 2018, we were there in November to December, and that was the time of the hottest time in Australia, probably ever. And all the bats dropped and died in Townsville, Australia. 30% of the bats, flying fox bats, all dropped. But we were doing a lot of measurements with these backpack sensors. We can tell them why they had exceeded, they had got a kind of stress level that it was exceeded, and the bats can handle it. So these are very useful to measure local and a small scale micro conditions that you will not get from a regular weather station or a satellite. It can never pick up these local micro scale this phenomena. So these are very, very useful, and we use them quite heavily. And Paramita uses in her class as well. She has her students hook them up to her cars, and they drive around to Manhattan or to Connecticut, and they measure local conditions as they drive around, and it tags them where they are. It has a GPS built into it, so it's quite
there is a GPS, and I was just mentioning that one of my students was an Uber driver, so he drives around the city. So he got amazing data in the airport and in Manhattan, especially in Lincoln Tunnel. So 3 probes can be attached to this at one time, and we can change the probes. And we also use this when we do water testing, to test the water salinity, temperature, everything. And
you can attach more, Paramita. You can attach more probes.
Yeah.
So those go plugged in, but these are wireless. These are
some of them are wireless. Yes.
So we can have those 3 attached as Paramita is showing you, and I have maybe 10 more attached by Bluetooth. So you can imagine a lot of different parameters at the same time. Yeah.
And the data comes like this, and there is a built-in GPS where later on we can plot it, and we can see where we traveled and how is the weather condition at a micro level, or if you're doing water, anything. So in Mumbai, it was interesting to see how carbon dioxide especially changed from a green park to the highway. So these are the things, students, they love it. And lately, Dr. Philip, you want to talk about the $20 one we got from Australia?
Sure. Let me just talk about Australia for a second. So Australia also adopted. The Australians also, they brought us, we did this in Spain first. We was in Mallorca doing these backpack weather station measurements. And the Australians, they thought it was very interesting. In Townsville, Australia, they won a smart city from IBM in 2011. So they brought us to Australia. They paid for my students and myself to come to Australia to teach them how to use these backpack, and they have bought a lot of them to themselves right now as well. So they started using backpack weather stations as part of their sustainability initiatives in that tongue of Thongsville. And it's quite successful. And they have gone to the next level and developed small sensors costing like $20, $20, using Arduino sensors, and they can measure temperature, carbon dioxide, light, sound. And these are, these are really small and very inexpensive, and it has a lot of wide applications around the world. So we're trying to work with them to kind of package these sensors in kits, and and they can apply them. If somebody wants to buy a sensor for temperature, humidity, you can get that sensor. If you want to buy a package with carbon dioxide, light, sound, you can buy that as well. So we're trying to work with Townsville to kind of package this with a company and to sell these sensors worldwide. In India, there's a lot of wide market in India for this as well. These sensors are very, very powerful. They even put them down into an ant's hole. You can put a sensor into an ant's hole, and the sensor sends information to the internet right away, to the free web, automatically with a Wi-Fi. So
how much is the first one, the instrument you show?
The one I showed, this is the logger, costs $329, and these probes themselves this is carbon dioxide, costs like $200, and each additional probe, like these other ones, cost $89. So you can get it for like $700. You can measure carbon dioxide, temperature, humidity and get this data logger as well for $700.
Can you have the GPS coordinates?
It has GPS logged in, so it has a GPS built into it. So even when we were in Spain and Mallorca, we walked through the mountains for 5 hours on 1 ton solar to there, and this is logging where we are in the mountains in Mallorca. So it's very, very powerful GPS system that can, give you accurate measurements where you are. As you walk and you can plot the data, you can see exactly where you are and what's the temperature, what's the humidity, what's the carbon dioxide, etc. Anywhere you are in the world.
Did you have a grant to fund your project, or did the college fund it all?
We scrap around. Parameter's very scrappy. Parameter got a grant from the president for $7,500. I got grants from other people as well for $40,000. I mean, so CUNY is very generous. I mean, and we involve a lot of students in these initiatives, especially when we travel abroad. So we have gotten funding from different pockets, none from NSF as yet, but maybe that's could be a good NSF grant, to do these in classes and become citizens. Every student becomes a citizen scientist.
Yeah, actually, when I have seen when they get it in the weekend and they keep this and they walk around in their neighborhood or wherever they're traveling and they get their data and GPS, they become it becomes their own thing, and they learn it more, because these are given to environmental science students and many of them are not a non-science major. So I think with this type of instruments, they get into more than theoretically telling them about climate change, this and that. I think this works a lot. But yeah, funding, sometimes we ask different professors whether they have extra money or not.
We beg, not ask, we beg them.
Yeah.
We beg a lot, we pass a hat around and beg a lot of people, But that's what you do as a professor, you got to do a lot of begging, and so we beg. We don't mind to beg. It's very good.
Do you have some evaluations from your program that you've put together and kept over time, that you have some data collected with how many people you've contacted and what they've done with them?
In terms of the assessment?
Yeah, and I'm thinking in terms of going forward, because what you have here is a proof of concept of a great science program. And you're talking about, working with students, NSF, one of their goals is to get more diversity in science, and you're out there doing it, getting citizen science and getting students interested in science. I would think you might have a good grant proposal going, especially if you have
we don't at the moment, but we put in locally with CUNY. CUNY has like grants like 40,000. I mean, we put in for Picaro for $50,000. We got a Picaro instrument. I think they have them in INSTAR. What is an INSTAR in Colorado? Colorado to measure these gases and from Antarctic ice core samples. So we got a Picaro, which is very high powered instrument. And again, these are much smaller, but the smaller grants can pick these up, because we normally need about 20 of them. And every time in chemistry department, we get like our budget is like $30,000 a year. So a lot of the budget goes to these instruments, these verniers, because it's used in more than one class. You have in chemistry, earth science, environmental sciences. So we do use our budget our allocated budget from chemistry department to buy these instruments, through that source. Yeah, but you're right. A nice opportunity will be to use a nice NSF grant and to grab in a much bigger way, in a much wider way in New York City and other places in the world to really, get a good handle on how these impact, our lives.
Can we use that for research? Sorry.
That students are interested in going into STEM fields or careers or coursework, things like that. It's pretty cool.
Yeah, we had a grant with Columbia. We are part of a grant with Columbia. If I take it one step backwards, actually, we had went to Australia. They had brought us here for a conference on ecotourism, actually. So we had proposed these as, like, the toolkit for ecotourism. So instead of walking around just looking at birds, why not walk at a backpack weather station and give some data, collect a lot of data and help us learn more about the environment as you travel, as you do touristy stuff, So that's why it was proposed in that kind of forum as a tourist for ecotourism. It's an ideal toolkit for the ecotourists, yeah.
What's the name of the company that had these $20 one?
It's called Vernier, Vernier, Vernier.
That's the $20 one too?
Oh no, the $20 one is put together by Australia. They buy stuff from China, a lot of things from China, and they put it together in a kit. And the parts cost $20 in total. But we're trying to build with Australia like a company that can package these things. Like if you want to get a temperature sensor and a carbon dioxide sensor, you can order this package, right? Or if you want something else, it can be packaged differently. So we're trying to work with Australia to push that concept of this, have a small company that can market these and sell these worldwide. But you can pick these up from any kind of hobby store.
Can you actually do research with this? How reliable the data, reputable? Can we actually use for like student projects, these kind of things? Okay.
Yeah, this has been published. Data has been published, with City College and Bronx Community College. It was published in, I forget exactly which journal, but Dr. Brian Van Holt, he was very instrumental also in helping develop these as well. So this has been previously published in New York City, working in the summertime, a couple of summertimes. So it's been published in reputable journals. And you can definitely get the instrument is very reliable. And again, it's used heavily in chemistry classes. And chemistry is very, you have to be very precise when you're doing like measurements for like pH or temperature measurements. So the instruments are very, very fine-tuned, and they're very useful in our classes.
So Paramita, can you send us the more information about the company? Like
Sure.
I have a grant I can purchase. It is a student experiential program. This will be awesome. It is in Belize in South America. We can monitor those microclimate when we visit.
Oh yeah, so this is great for that. This is absolutely great. I mean, the pattern. I mean, we used before the plastic, what we put the sensors on, the sensor pads were built in Australia. We used a 3D printer to print them in Australia, actually. So before we used cardboard to put the sensors on, but then we got a little more advanced and we started using these plastic 3D printed sensor pads from Australia. That was their contribution to the project. So it's been very useful, and we can provide that file to you. That's just a 3D printed file. We can provide that file to you. So you can also print them over there. These pads, we can put the sensors on these pads as you walk around on your backpacks.
Awesome.
So definitely, Paramita will be sending that more information to you guys.
Thank you.
Thank you for being here, and it was great to see you again.
Yes, Louise. I hope that come. How is Elaine Hood? She's still around. She's still with the Antarctic ASC. Elaine.
Elaine, yes, she is.
She's still there.
Still doing it, yeah.
Oh my gosh, still in Antarctica, huh?
Yeah.
I need to come there sometime. Maybe one day I'll come to Antarctica if I get invited. I'm PQ'd. I'm physically qualified. Don't worry. I'm in better shape now.
That should be your next step for sure.
Yes, I love that. I love to have that opportunity. All right.
So
good to meet all of you, Carol, Renata, everybody, Kay, Bill, everybody. Good to meet all of you. I'll see you guys very soon again. All right, in the future sometime.
Thank